Hi, my name is Harrison Butker, and today we will be looking at Lab 2, Motion of a Falling Object. To begin, we will use a software called Tracker to analyze the falling motion of an empty Powerade bottle. We will then use a software called Python to make a computational model based off Newton's second law of the falling Powerade bottle with and without drag force. We will then use Google Sheets to look at a position versus time graph without drag force from our computational model, a position versus time graph with drag force from our computational model, and a position versus time graph from our experimental model. We will then answer the following what does it mean and what if questions that will be posed later. When analyzing the motion of the falling Powerade bottle, I first had to give the Tracker software a reference of length. Since I am 6 feet 5 inches tall, I made my height 1.956 meters. I also had to rotate the axis so that the y-axis remained in the middle of the bottle throughout the entire time interval. Once we have plotted the position points throughout the time interval, we are ready to see the motion of the falling object. Here is what the position versus time graph of the experimental model looks like. We now go on to use our Python software to look at the computational model based off Newton's second law of the falling Powerade bottle with and without drag force. The first piece of data I entered into the Lab2 starter program was the mass of the empty Powerade bottle, which was 0.036 kilograms. I then made sure the initial velocity of the ball was 0, since it was being dropped from my hand. Since we are looking at the computational model without drag force first, our proportionality constant is set to 0. I then entered in the time interval, which goes from t equals 0 to t equals 0.5, and the formula for the gravitational force on the bottle, and set that as the net force on the object. The time interval goes to 0.5, and the gravitational force equation is W equals negative ball dot m, the mass of the ball, times g times j hat. And then even though we have the drag force equation in here, B is set to 0, so our F net is only the gravitational force on the ball. So here's what our computational model looks like. Now, to look at a computational model based off Newton's second law of the falling Powerade bottle with drag force, I have to insert the equation for drag force. This equation is F sub d equals b times the magnitude of ball dot vel squared times j hat, and then F net equals W plus FD. From this information, I have to assign a number to b, the proportionality constant. I did this by plugging in different values of b until the final position of the computational model was equal to the final position of my experimental model. As you can see, when you run this with b equals 0.0041, you get a final position of negative 1.174 meters, and from our experimental data, our final position is negative 1.174 meters. Using Google spreadsheets, we can analyze the three graphs of position versus time. As you can see, the graph of model without drag force is below the experimental graph, except for the time interval between 0.3 and 0.4, right here. This could be due to plotting errors. You can also see that the graph of model with drag force is above the graph of model without drag force, and that is because our computational model with drag force isn't going to have as high of an acceleration, thus causing the object to not travel as far as the object without any drag force. Our experimental model looks more similar to the graph of model with drag force, and that is because during the experiment, drag force was present. The what does it mean question asks, examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? By looking at the velocity versus time graph from our computational model, we can see that the graph of velocity without drag maintains a constant acceleration, while the graph of velocity with drag begins to decrease in acceleration and approach a terminal velocity, which has an acceleration of 0. The what if question asks, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? By looking at the terminal velocity graph, you can see that they both reach the same terminal velocity, which has an acceleration of 0. This terminal velocity is negative 9.276 meters per second.